I'm ready. I'm ready.
You ready? Okay. So welcome everybody to this first morning talk. So it's my pleasure to introduce Xiaochuan Yang. Sorry for the pronouncement. And so he will talk about fractality and multifractality of Markov processes in a joint work with different authors. And one of the authors is the co-organization of this semester at INI. Okay, go ahead. Thank you.
Thank you, Dalia. Thank you very much for the introduction, and really happy to be here to give this talk. Also today is it's International Pi Day, so it's a good day for celebrating mathematics. The topic is a fractal geometry of some exceptional sets related to Markov processes. So I'm not going to assume anything. So I'll try to make this talk as self-contained as possible. So I'm going to pretty much bore some of you in the first section by introducing what is a fractal and what is a fractal dimension. So before I do anything, I want to introduce this really basic notion. So if we have a set, we want to talk about the Hausdorff measure. D-dimensional Hausdorff measure, a set in RD, for instance, then what we should do is to first consider really a covering. So A is covered by union of sets, let's say VI, I from 1 to n, and every set has diameter smaller than equal to epsilon. And what we should do is to take the sum of the VI, so diameter really, of the VI's to the power D. I from 1 to n. Then we take the infimum of all such covering. So this gives us the, not the measure, because we still have the additional requirement that all the sets has diameter smaller than epsilon, but more or less, if we take, let the epsilon goes to 0, obviously this quantity defined as such is monotone, the limit is going to exist. And this limit is what we call the Hausdorff measure of dimension D. So of course, this is also the big measure up to a constant. But this definition is really general. We can generalize this. So this covering is okay, but we can generalize this power to a fractional order so that we can talk about the Hausdorff measure of dimension S. So here S could be between 0 and D if we consider a subset of RD. And so more generally, we can consider matrix space, because all we need is a matrix, right, to measure the diameter of some set. So definition very general. So from now, I'm going to restrict myself to the case of RD, and so there's the notion that I have to introduce, which is the Hausdorff dimension. Hausdorff dimension of a set is defined to be really the smallest s such that hs of A is finite, or the sup of S, h of S of the set A is equal to infinity. So the logic of this is because it's for a fixed compact subset of RD, we can draw a figure of the Hausdorff measure of A, S-dimensional Hausdorff measure of A as a function of S. So if dimension, if S is too small, then it's gonna be infinity. Otherwise, it becomes 0. So this threshold value where it's not 0, not infinity, or it could be both actually, but there's a threshold value where the value is uncertain. We call it the Hausdorff dimension of A. So there are so many versions of the dimension. The most classical one is Hausdorff dimension. There's also packing dimension. There's upper and lower box dimension. So but I'm not going to talk about that today. So one very simple example. So it's considered a contour set. So everybody learned this from measure theory. So we start with the interval 0, 1, then we remove the divide into 3 pieces, we keep only the left and right. And then this is the 0th level, this is the first level. You do the same thing, the same procedure, remove the interval in the middle, and so on. This is the level 2. Keep this going. And then eventually we are going to define the set, which is the intersection of the union I in all this sort of small intervals of the level n. All right, so it's a link strip type of set. And this turns out to be a fractal. And I'm going to illustrate. So the Hausdorff dimension of this set is log 2 over log 3. So now I'm going to introduce two basic principles. So everybody use this principle if you want to calculate the Hausdorff dimension of something. That's the first principle, let's say. So I'm going to also use this in the stochastic setting. So I think it's of use to introduce all this. The first is what I call a covering principle. So covering principle says the following. So if you have A is a compact subset of Rd, and you have a family of sets, which is a partition of the Rd, and these are decomposed of cubes of diameter for, say, Rn. So the condition we require for Rn is that Rn plus 1 over Rn is essentially a constant. So bounded from above and below by two constants. So if the number, if we try to cover the set A with all the small cubes in the family of sets of Bn, and if we count this number, we have some order, something like Rn to the negative alpha. Rn goes to 0, so this guy goes to infinity. So from here, we conclude that then the dimension of the set will be smaller than or equal to alpha. So this is pretty simple to see. So if you compute the Hausdorff S-dimensional Hausdorff dimension of the set A, naturally it is bounded by, if you take all the scale sum, take sum over all the scale, then you have this, let's say Rn is essentially 2 to the n. Doesn't matter. So this condition says that if we do the counting, we have n alpha intervals. Each interval is of the length 2 to the negative n. And we need to take to the power s, which is this dimension here. So now I'm just using the definition. So this thing will be finite if s is larger than alpha, geometric series. So this would imply that the Hausdorff dimension of A will be bounded by alpha, this end of the theorem. So really, really simple, but it turns out to be extremely powerful in many situations. I'm going to illustrate this later. So the second principle is what I call a mass distribution principle. All right, so this is for computing the lower bound of Hausdorff dimension. So if A is a compact subset of Rd, and if assume there exists a measure, a probability measure, mu, such that with the support of the measure included in A, and that there exists a constant such that you have a sort of a scaling, power law scaling condition, C r to the alpha for any r less than equal to 1, then the Hausdorff dimension will be bounded from below by alpha. Okay, very good. So this is very simple to prove. It's just one line. So what we need to do is to realize that, okay, so probability measure and the support is included in A, so the total mass is A will be 1. It's bounded by any covering, let's say, okay, Bi, and by a sigma summability of a measure. So what we have is the sum of all the measures. But since we have this scaling condition, we see that it's bounded by C times sum, then R to the okay, so it's going to be the diameter of Bi to the power alpha. And we can bring this to the other side. We realize that for 1 over C, which is strictly positive than 0. It's the lower bound of whatever this is. But this, if you take the infimum, we have the host of measure, alpha dimension host of measure. So since this is not 0, it says that the host of dimension must be larger than alpha by the observation made in the first slide. Okay, very simple. Again, very simple yet extremely powerful. And we're going to see, let's just, before I do anything about stochastic, the last thing is I do in this section is the example. So I claim that host of dimension of C is, which is the constant set, is given by log 2 over log 3. There are two directions. We want to show the upper bound. We want the economic covering, and here we can just count the number of i's, which is I intersecting this. So let's say if I take r is 3 to the minus n. From this picture, from the cartoon, we see that the length of the scale n, each interval of the length scale n should be 3 to the negative n, and there are in total 2 to the n intervals at this level. So if I choose like this, then I'm going to have 2 to the n, which is 3 to the n log 2 over log 3. So this is what I want, right? So 1 over Rn. And this is the power which gives us the upper bound for the host of dimension. And if we want to do the lower bound, we need a measure. So the point of using the mass distribution principle is to construct a measure, a probability measure supported on A, such that the scaling condition is satisfied. So I'm going to distribute my mass starting from 1 into level 0. At level 1, I'm going to distribute it uniformly to the left-hand side and right-hand side. So this is the mass, not the length. So then the next level, a quarter, and so on. So eventually, I'm going to converge to a measure on 0, 1, which on every dyadic interval can just take the sum of all the mass, which leads to dyadic intervals. So every we can just take a sum of the mass on the interval which is non-empty. So it can be extended to all the Borel sets, obviously. And this condition B of x, let's say 3 to n is bounded by twice 2 to the negative n. So this is the size, this is the length of the interval, and this is the mass that we have. So again, we have the good relation, right? So this essentially is 3 to the negative n and log 2. Lower bound also holds. This is very simple. All right, so I hope everybody now is equipped with all the necessary material to understand the rest of the talk. And I'm going to introduce some random fractals associated with Markov process. And so Markov process, so here I mean continuous time Markov process with values in order, so continuous in time, continuous in space. So my focus will be the range set and the inverse image, the two kinds of set. One particular example of this is the level sets, obviously. So I'm going to interested in the uniform dimension results in the sense that I would like to have a formula for instance, the range for dimension of range for Markov process equal to some formula in star for all the Borel sets E with probability 1. And on the other hand, obviously, and you can ask the following question exactly the same way. So is there a formula for given Markov process? Is there a formula which such that the range of the inverse image has a formula uniformly for all the E? And this will be turned out to be useful in many applications that I will mention. Okay, maybe just one application that I will mention. Great. So this is the kind of thing I'm interested in. And for Markov process, there's really a key tool or a key property. If we talk about Markov, then obviously this is is implied. So what I need is really the strong Markov property. By that I mean f of x, if you take a shift of the path by a stopping time, take the conditioning on the filtration generated by the process up to the stopping time, then this is given by the condition expectation of the process that started with xt. X is the process, t is the heating time, t is the stopping time for all stopping time. So there are so many examples, interesting examples of stopping time. For instance, we can talk about the heating times, which is I would denote by tau, and this is the infimum time such that the process xt hit a certain set b. There's so-called the exit time. For instance, this will be t when x escapes a certain set d. So then these two sets of stopping times will be of use to our study of the range and inverse image. So now I will go to the setting where I talk about range of Markov process. And okay, so the goal is to cover, if we want to do the upper bound, I'm going to use my first principle. Principle number one is covering if I want the upper bound. So I want to cover this image of Markov process X, and we know that E will be covered by so E if the Hausdorff dimension so will be covered by E plus epsilon. Okay, so this really is the first claim is really deterministic. There's nothing random about it. So any set of half the dimension D of the set, dimension E, we can, if we only use balls of diameter 2 minus n, then we need this many to cover it for n epsilon. Okay, so this is upper bound, and so which means that really we are, instead of interested in any set E for a particular scale, we are just interested in intervals. And there are this many intervals to be concerned about. So, so the idea is to cover really X of an interval with the correct order. Correct order in the sense that it gives eventually the sharp Hausdorff dimension in the upper bound. But also we want uniform in I, because eventually what we want is this result to hold uniformly for all the Borel sets. Okay, so that's the goal. So how do we cover this? So I'm going to start really with a simple example where you have a Brownian motion. So in the case of a Brownian motion, you consider a small interval of size, I don't know, doesn't matter. So start from here, and we know that Brownian motion oscillate, but there's an upper bound for the oscillation. So really the growth of a Brownian motion is I to the 1/2 up to a log. Okay, so we can make this precise, but I don't want to. So up to log. We know that in order to compute Hausdorff dimension, the log term doesn't matter. What really matters is its power. So so growth will be I to the 1/2, which means that if you want to cover the range in this interval, so this the range is here, and if this is 2 to the n, this will be 2 to the n over 2. So this is a good hint, and it means that we can really the number. Okay, so the number of intervals of size the number of intervals of size 2 to the negative n over 2 will be of the order 2 to the n. So which gives you an upper bound of 2 for the Hausdorff dimension, because this is going to be the square of negative square. This is the negative square of this term. All right, so this is pretty simple. And in case of alpha stable, so what do we do? We also know that the growth of alpha stable is like I to the 1 over alpha. And this is really not hard to see if you think about this scaling relation of the stable process. And can we use the same argument meaning that can we cover the range of the stable process by using intervals of this size, and eventually is it going to be exactly 2 to the n of them to cover it? The answer will be no. So this is a too naive approach, and the reason is that there are jumps. So it could happen that in this interval of length I, so you go somewhere, maybe this is x to 1 over alpha, say, but in the middle it might jump to another thing. Can you really cover everything by this single interval of this size? It's impossible. So it's going to happen. The jumps are going to happen. So what do we do? So this is where the Markov property comes to rescue. So we're going to consider the exit time. So we define exit time to be t minus x0 larger than 2 minus 2 alpha. So that's for the let me draw a figure here. So let's say we have a pause, which is quite irregular. Okay, so this is our interval. This is our first interval, or any interval in the middle, and it jumps quite a lot. And what we are interested is the first time when it hits. For instance, this is the size of this interval. The first time it exit the interval of this size. So the first time occurs when this thing, so in this example, tau t will be just here. Tau 1 is just here. And after we jump, we're going to define this release tau. We start, I'm not going to write it down. So we start from here. This is where the process is at the stopping time, tau 1. So I'm going to introduce this another window, and the first time it exits, I'm going to call it tau 2. So by doing this recursively, we define a sequence of stopping times. And the beauty is that now, by using this random time interval, so we can cover it with precisely the intervals of this size, the range of these processes. For the stopping, from time 0 to tau 1, I cover this piece. From tau 1 to tau 2, I cover this piece. Okay, so the question is, how many stopping times are there for in a particular interval of side length 2 to the negative n? And this is where I can use my Markov property. Let's say I want to see k stopping exit times within an interval of side length 2 to the negative n. Obviously, this would mean that, okay, so tk minus 1 is also smaller than this. It's a bit smaller. And this is smaller because, it's increasing stopping times. And also, from this point, I also know that xt minus tau k minus 1 and t larger than tau k minus 1, smaller than 2 minus 1. This is where the length of the interval, this is what happens after this. So what I require is that after k minus 1's exit time, then I start from here, my next stopping time, and next exit time will be still smaller than 2 to the negative n. Okay, and so this is what I want. Alpha, let's say. So I'm a little bit flu here. Actually, I want to have some flu plus minus epsilon. Okay, so doesn't matter. It's good enough for intuition now. So what this means is that we can use our Markov property at the stopping time tau k minus 1. So we can recursively apply this argument. We can actually see that this guy and this guy will be independent in the case of Levy process. And then we have this guy, which is just 1 order smaller than what we start with. So this means that eventually what we have is the probability of a supremum of t less than 2 minus n, xt minus x0, larger than 2 minus n alpha, to the k. All right, so there's a known result. So now we are come to the exit time asymptotic, or this is kind of a large deviation estimate. So we know the typical scaling of this should be okay. There should be over. Sorry, something like that. Typical scaling of this should be 2 to the negative n over alpha. If we plus minus epsilon in here, we see we're going to have a large deviation event. So this will turns out to be it's a separate problem. I'm going to tell you the answer. There exists a certain delta which is independent of everything, such that this eventually is 2 to the delta times k. K comes from here. The point is, if you take the sum over n and consider the probability that there exists an interval of side length 2 to the n, and xi is not covered by k intervals or k cubes, because the space k cubes of the side length 2 to the negative alpha and alpha, and so this just means that you have something like this happens with a particular k. If you take the sum, you see that there are in total 2 to the n such intervals, and 2 to the negative delta k, which is eventually goes to finite. The sum is finite. Lorinczi tells us that for all the scales, actually for properly chosen k, k is larger than essentially 1 over delta. If this is true, then all the interval here, all the dyadic interval here is covered by, there are at the most k exit times. So the number is essentially the same as the number of dyadic intervals, which is 2 to the n times k. All right, so this gives us the upper bound. So as such, we know that we are going to cover xe first by taking uni over all the scales, and there are this much intervals needed to cover the set E. This is the number of dyadic interval we need to cover set E. And for each such interval, I'm going to cover it with exactly k intervals coming from the k hitting times in the small interval of the dyadic interval, Qij. So diameter of the Qij is 2 to the negative n over alpha plus epsilon. Okay, so now we can compute the Hausdorff measure of this set by taking the sum over all the scale, I, j, and so each interval to the power s. To the power s. And we know how many i's are there, how many j's are there. So eventually it brings up to n 2 to the n dimension e minus s over epsilon. It is going to be finite if s is larger than alpha times dimension of e. So this gives us the upper bound for the Hausdorff dimension. It is the sharp one. And since I take the I have a uniform result for the covering of each dyadic interval, this is also a uniform result. So this holds true almost surely. Okay, so we see that the hitting time is really the exit time is really the key here. So I want to comment on generality of this result. So now, in the previous example, what I did is really for our stable process, but this can be generalized can generalize very easily to more general Markov processes. And for the exit time asymptotic, there are results. We can always link it to the symbol of the Markov process. And this is the approach described in this Seuret book by Boscher, Schilling, and Wang. And for the V-type processes. And so there's the recent work of Sun, Xiao, Xu, and Zhai. They work out all the details of the previous of this covering arguments for the upper bound. and precisely by making use of some exit time asymptotic. So the important message I want to say here is that the exit time asymptotic eventually gives you the upper bound for the range. That's the other things are easy to generalize. Markov property. This is it's Markov property. So that's not difficult. All right. So now let me go to inverse images, and there's a little bit of caveat. So in order to consider the dimension of inverse image, we really need the process to hit at least hit points. Otherwise, this kind of thing will be empty. So the caveat is that we need a process hit points. So in case of stable, we really want alpha to be larger than 1, and the dimension of the space will have to be in 1 dimension. So we consider recurrent processes. And typically in this case, it will be the case that the inverse image will be alpha interval, because you can, same arguments, you can always cut your set into small pieces at a particular scale for covering the set, the F, then you go back. So for every interval, we do this covering for just the X inverse of an interval. So this will typically be unbounded. So it's not going to be true that the inverse image is covered by a finite number of intervals. So even if I restrict myself to a particular interval, 0t, so let's say 0, 1, doesn't matter. So even if I restrict myself to a finite interval, this will still explode the number of time I get back to. It will still explode if I take this, if the size of the interval gets smaller and smaller. Okay, so with high probability, let's put it that way, because there's the event that you never visit this interval in a long interval, but that's a different story. Okay, so I'm going to draw a picture again for illustration. So what I do is I have this interval of side length 2 to the negative n. Okay, so I'm interested in where the process passed by this. For instance, something like this happens. Okay, so I'm interested in the time where, if I want to cover the inverse image, this inverse image corresponds to precisely this piece and this piece in this simulation. And so I'm going to be interested in how long this piece is and how long this piece is, the time interval. So analogously, I'm going to define this heating times. So tau I heating times. Instead of defining in mathematical words, I'm going to just do drawing again. So the first time it hits should be here. This is my tau 1, and then I'm going to need an interval to cover it, of course. And what is the wise choice of length of interval for this piece? Okay, again, so in the case of stable process, we know the local growth. So the sort of wise choice will be something like if this is 2 to the n, so this should be of the length 2 to the negative n alpha. Okay, so after this amount of time, then I start from here. So I don't know where I am. Maybe I'm here. And I'm going to see the next time I will hit again this interval. So that's going to be here, tau 1, tau 2. And again, I stay for a while. Let's say it's 2 to the negative n alpha. Maybe I'm still in the interval, then doesn't matter. From here, I see that I'm already in it. So immediately I'm going to include the next interval. Another 2 to the n alpha. Then I'm out of it. So next time I'll hit, then it's out of this picture. So the question is, if I fix a time, which is t, how many heating time are there included in this interval? If I know this, then I have a covering, because I use intervals are all the same size, and all I need to do is to count how many of them in order to cover this set. So that's again the first covering principle. So what we can do is to cover this set I 0t by all the heating times I such that tau I is smaller than or equal to t. And every time I have a heating time, I'm going to include the interval of size 2n alpha, plus minus epsilon for this. Okay, so this is the strategy. So the remaining thing to do is to count how many of them. And here again, we can use the Markov property, which eventually gives us the counting result. Of course, up to some separate estimate. So the key here is that, again, so this will be bounded by some tau k minus 1 smaller than t minus 2 minus n alpha, because you have one more heating time after this. You need at least this much time for that to arrive. And we know that by the Cadillac property of the process, it must be x the heating time, k minus 1 heating time, must be included in the set I. And also xt hits I during the time interval tau k minus 1 plus 2 minus n alpha t. Okay. So we can apply Markov property at this starting time, and eventually what we end up with will be the xt hit, say, okay, so there's a little okay, let me just not hit I in 2 minus n t, n alpha. Okay, so my process is going to hit the interval, in this interval. So let's consider, since I'm going to assume this is just stable, so to use some scaling argument to make this simple. So I can multiply, and this is the right scaling to do in order to have exactly the same process. And from here, I see that the xt, I can translate this, right? This multiplied by I makes the interval becomes a macroscopic level. And the xt hits the interval minus 1, 1 in the time interval 1, 2 to the n alpha times t. Okay, eventually to the time k by recursive arguments. And what we can do is okay, I'm a little bit short in time, so probably I will not give the full detail. But we can immediately see that this will be the deal is that this guy should close to 1. In a very long interval, my process will hit this minus 1 interval because it's a recurrent process. It's gonna come back. So this is going to close 1, so we need to really quantify how close to 1 this quantity is. So we consider a complement and bound from below the complement. Let's call this guy Pn. So the complement 1 minus Pn is the consequence of the fact that if you have a process at time 1 it hits 2, 3, and at time so then you can use again Markov property. If you have the process starting from say 3 and your time hit a small minus 1, 1 interval in this time from 0, not from 1, or 2 to the n alpha t. If this happens, if your process satisfies this property, then it is not going to hit this. So what I mean is not hit this guy in the interval. And this is precisely the heating time asymptotic. So this is basically tau 1. So this is the heating time asymptotic, which known in the literature. You have a 2 to the n alpha which is the length, which is this size of the interval. For a very long time, you don't hit the interval. This probability scales like a -1 minus 1 over alpha. As I said, alpha has to be larger than 1, of course. Okay, here actually I need it to be 1 alpha larger than 1. But there is a log sort of a version of this in the case alpha is. And this is due to Portland-Stone. So again, a reduced computing Hausdorff dimension, upper bound or counting problem, counting how many intervals do I need to cover the inverse image to a probabilistic estimate, which is the hitting time asymptotic. Okay, so this shows, so this time I'm gonna skip the detail. This shows that what we really need, the K has to depend on N. The number of hitting times in the interval behaves like 2 to the N, alpha minus 1 plus epsilon with high probability. So eventually it's gonna happen for all the large scales. And with this counting in mind, we can have the, with this counting in mind, I can have, I can have the upper bound, which gives the, if you consider alpha stable process, inverse image, and the formula is given a 1 minus 1 over alpha plus dimension f to the alpha uniformly for all the f with probability 1. So uniform dimension result is obtained, and this is due to Song, Xiao, and myself, and this whole covering argument was new, and later on, together with Hangzhou Park and Xiao and Yimin Xiao, so we did a Levy case, so alpha stable case due to the first paper. So again, I'm going to comment on generality, more of an open question. So I would very much like to extend the whole approach. So Markov Property is nothing. So so we have a sort of a proof scheme for computing the Hausdorff dimension. By the way, these are sharp formulas. We have lower bound as well. So so the question is, how far can we go from, so just Levy, for not just Levy, go from Levy to the more general Markov process, for instance, stable light processes, even constant order stable light processes. So we really don't know. And there are two open questions. So open question number one is actually even in the Levy case is not known. So the inverse image formula for the case Cauchy process is not known. That is because we don't have a lower bound. The upper bound works very well, and truly the question is, can we prove that the inverse image of this alpha 1 is a little bit confusing if you don't say it. Alpha equals to 1 stable process, inverse image of any set has also dimension same as dimension of f. So this is what tells us if we plug in numbers, alpha equals to 1. And we do know this, we know the upper bound, but we don't know the lower bound. So I didn't say how we prove the lower bound for previous cases. That's really the second principle, which is the mass distribution principle. So we need to construct a measure, and for processes, stochastic processes, there are natural candidates. For the range, we can use the natural occupation measure, and for the inverse image, the good measure is really the local time. So for Cauchy process, there's no local time. So we don't know how to construct a measure just supported on the level set, for instance, of Cauchy process. Although Cauchy process does hit points. Okay, so this is the first open problem we don't know how to solve. And the second is that obviously Markov, more general Markov setting, even the stable-like case. So what we're missing here is the hitting time asymptotic. But the rest of the argument is it's okay. So we need a version of the Portland-Stone theorem in the case of the Markov setting. By the way, I should have mentioned that. Sorry, terrible. I should have mentioned that our results on the V process here is based on. Okay, it's very hard to. It's very hard to pronounce. I will not try. These guys remarkably proved the heating time of sample six for the V processes, for classical V process, and our results are really based on this. Okay, and we need a asymptotic heating time of sample analogous result for of this type to general setting. So I realize I don't have much time now, so I will, but still I would like to mention at least a little bit of multifractality, because that's in the title. So multifractality, and why do we care? So I say a function Rd to R is multifractal if I observe a kind of Holder exponent, Holder condition, but every time if I change the base point T0, I'm going to observe a different Holder exponent. Holder exponent is the largest alpha we can put in here for a fixed time. Okay, so the key is that if your Holder exponent doesn't change with time, we call it a monofractal function. And the typical example is really this fraction invariant motion. So the whole class of fraction invariant motion is like that, and a lot of Gaussian processes. And obviously there are variations from deviations from the Holder condition, but the correction is only logarithmic, so we don't really care. For the V process, this thing really changed rapidly this time. So what we call a multifractal spectrum is the Hausdorff dimension of T, alpha f of T, Hausdorff dimension of the set of time T such that the Holder exponent is equal to a particular value, alpha. And we want to find a formula for all the possible alphas. And the whole thing can be generalized to measures. In the sense that you can talk about a scaling of this type. If you consider the measure of a ball of small radius power. And this power changes with time, that is called a multifractal measure. Okay, so why am I talking about this? Because there are some link between the uniform dimension results and the multifractality. You see, when you think about occupation measure, you think about occupation measure, which is defined in this way. Think about occupation measure. If we want to study multifractal analysis, for instance, the Holder exponent of this measure on every point, then it is often the case that we can construct a sort of exceptional sets on the time interval. On the time, so subset of the 0, 1, and then map it to the space such that it satisfies certain spatial property, the Seuret property for the occupation measure. And this is where, because the sets are actually random sets, construct a subset exceptional time sets, map it to the space. We really need the uniform Hausdorff dimension results to make this work. And this is for instance, I think I still have time to quote at least some reference. This Hu and Taylor's result, which is concerned about multifractal analysis for the occupation measure of subordinators. And Seuret and myself, we have considered occupation measure of variable order stable light processes, which is also interesting. So it's kind of a counterpart of the subordinator to the variable order stable case. And then we make use of these kind of arguments. So, okay, only the last part I have is really the multifractal spectrum of the type process. And I will not have time to do this. Let me just mention that this is a joint work with Joseph Lorinczi. Very sorry, Joseph, I'm not going to have time to talk about this today. And also part of this is my own work during my thesis. So there is a very good connection of this so-called P-phi-1 process or P-phi-1 process. Or ground state transform the process, which is related to Schrodinger non-local Schrodinger operator, and then from here we can actually find we can find the stochastic processes associated with the ground state of this kind of process of this kind of operator, and we study multifractality results for these processes. And in more classical setting, earlier work of myself, I did multifractal analysis for so that's the process I studied with Joseph, and that's the process I studied myself. Okay, with that, I'm going to end this session. Thank you very much for your attention.
Are there any questions?
Maybe I can ask one.
Yeah.
So we already discussed this a bit, but regarding the formulas for the Hausdorff dimension of the inverse of a set, when you have a general Levy process. So you mentioned you also have some results in this area, but I guess in this sense, you don't have a uniform upper and lower bound for all type of sets, but some upper and lower bounds.
Yeah.
Yes. So can you tell us a bit more about the generality of these results in the sense, what types of characteristics does it?
Yeah.
So for which types of characteristics do you have generalizations?
Yeah, so the generalization is, so there are two types of, so always we have two parts, right? So you need an upper bound and your lower bound. So for the upper bound, really the argument we need is the heating time asymptotic. And this one, as far as I know, is only obtained in the case where you impose some sort of a upper and lower scaling type of condition on the Levy exponent. And for the lower bound, what we need is the regularity result of the local time. So spatial regularity of the local time, in the sense that, so this stage, so you have a local time which is a process of two parameters, space and time. So so what we need is the spatial regularity. So okay, spatial or temporal. I think temporal. Sorry, I think it's temporal. Yeah, it's because we're interested in the level set. If you fix an x, then this gives you the zero set. This is supported on the zero set of the process, and what we need to know is the regularity. This is actually a measure, increasing process associated with the measure. We need to know the regularity of this measure and apply this kind of argument. And for this, we can compute the moments and so on. This depends really on different types of asymptotic. One is if you take a lead sweep or something, and you have one exponent in your Levy exponent, another is taking in for something. So it's not very likely that I need to check the details, but I think it's not very likely this kind of uniform dimension result can hold for everything, for all the Levy process. So you really need some conditions.
But basically, you need this scaling in terms of between two power functions.
Sort of. Yeah, I think that's true. I think that's true. Yeah, sort of scaling. Yes. Yes.
I was waiting on your talk to get to
Multifractal. Yeah.
Incidentally, there is some connection with the work I've been doing with Seuret recently. We've been looking at Markov semigroups or families of Markov semigroups where generators depends on time. You can think about some examples in the way that you are looking at the measures which are better than Xiaochuan. In this case, you may have some better properties in hyperconductivity, and to get just hyperconductivity, you take appropriate root of the generator. And in this way, you get families where you get what we've been talking about. This should be nice examples of the process. You don't take separately the root of the Laplacian, but you take the root of the operator. So it is nice to see it.
Okay. Yes. Thank you. Thank you. Yeah. Yeah. Just in about 3 weeks, I'm going to talk about at the James seminar. If you're here, and we'll be talking about multifractal analysis. Very interesting. It'll be online also.
It's scheduled on the 13th of April. His next talk is scheduled on the 13th of April.
Yeah, thanks.
Yes, I wanted to ask about diffusion. Is it correct that everything which is correct for Brownian motion is automatic and it's the same for diffusion?
Not necessarily. So you think about diffusion, you do have this downstream trust theory, which tells you that you can connect the martingale back to right motion. But it's the case you are in a good setting if the diffusion coefficient is not degenerate.
Yeah, so
so
non-degenerate diffusion,
yeah.
all your result from Brownian motion basically.
Yeah, then then will be true. Yes. So I didn't mention, but I would really like to. I would like to mention the one open problem I have for the multifractal analysis is that if we consider some degenerate Young diffusion coefficients, which can be 0, then this.
Yeah, then every single constant.
Yes.
Okay, thank you very much for so an interesting talk. So if there are no more questions, we meet back at 2 for the next talk.
Thank you very much.
Thank you. See you.